Welcome back. This is going to be part 3 of our discussion of Chapter 2 on probability. This will cover Section 2.6, Conditional Probability. So we'll start with an example. Let's consider mortality on the Titanic. In particular, I've got data from the Titanic sinking back in the early 1900s, and the information is categorized by men, women, boys, and girls, and those who survived versus didn't survive out of each of those categories, along with associated row and column totals. And we'll define 2 events. The first event will be that a passenger is male. We'll call that event M. The second event is that the passenger survived. We'll call that event L for someone who lived. I'm avoiding using an S because we've been using S to describe our sample space. We're interested in asking a variety of questions that differ in their language, and we'll see that they also differ in their outcomes in terms of survival rates for men, depending upon the way we ask the question. So let's get started. Let's start by asking what is the probability that a randomly selected passenger was a man and a survivor. In order to do this, what we have to recognize is that the probability we seek is the probability of M intersect L, because remember that corresponds to outcomes shared in common between event M and event L. So to do this, what we'll do is look for the intersection of the column for men with the row for survivors, and we see that there are 332 men who survived out of the 2,223 total passengers. This gives us a probability of 332 over 2,223, which is approximately 15%. Next, we ask, what is the probability that a randomly selected survivor was a man? In order to answer that question, what we're looking for is first isolating the survivors, so we focus only on the row corresponding to survivors, and we notice that there are 332 men out of the 706 total. Now, you'll notice that I've used a slightly new notation here. In particular, this notation P of M with this vertical bar, then an L. We're going to use this notation to represent the probability of M given L. So that vertical bar there represents the word given, and the idea is that we're first restricting our sample space to survivors only, and then we're looking to see how many males survived out of that restricted sample space of 706 survivors. So we get 332 out of the 706, which is approximately 47%. So it's worth noting that this question may also be phrased as, what is the probability that a randomly selected passenger was a man given that the passenger survived? Next, we ask, what is the probability that a randomly selected man was a survivor? In this case, we first are restricting ourselves to a sample space of only men, and we see that 332 of them survived out of the 1,692. So we'll say then that the probability is approximately 0.196. And again, I'm using this notation here that has the vertical bar in there to represent that first we're restricting ourselves to the men, and then we're looking at the probability that someone survives. So we call that the probability that a passenger survived given that the passenger was male. Next, we'll consider the question, does it appear that the rule women and children first was observed in terms of survivors of the Titanic? So what we'll do is we will consider non-males. If we look at the non-males, so namely women, boys, and girls, what's the probability that that passenger survived given that they were not male? In particular, we're looking for the probability of L given B complement. Oh, actually, that shouldn't be a B. That should be an M for males. So the probability of M complement, so there are 531 non-males, and 374 of them survived. Namely, we took the sum of 318, 29, and 27 to get the 374, and 422, 64, and 45 gave us the 531, and we get approximately 70%. So it does appear that the rule was observed, since 70% of non-males survived while only 20% of males survived. What does this mean for us? Well, we have 3 different probabilities here, one approximately 15%, one approximately 47%, and the other approximately 20%, and each of them relate on some level to the survival of men on the Titanic. and each is true depending upon our point of view. So the moral here is that confusion can arise when probabilities are stated without reference to the sample space. So what we need to do is make sure our language is specific enough to define the sample space of interest, because depending upon the kind of question we ask, we could get any one of those type of 3 answers above when discussing survival rates of men on the Titanic. So now we'll formalize that example into a definition for conditional probability. We'll say if A and B are any 2 events in a sample space S and the probability of A is non-zero, then we'll define the conditional probability of B given A to be as follows: the probability of A intersect B divided by the probability of A. And again, we're using this notation here, probability of B given A. Remember that vertical bar means A. So what we're saying is we're assuming A has occurred and we're looking for the probability that B occurs, knowing that A has already occurred. So if we revisit the Titanic example and we apply this conditional probability formula, say we try to apply it to the probability that a passenger survives given that they were male, we'll compute the probability of the intersection of being male and surviving with dividing that by the probability of being male. So remember, there were 332 survivors out of all 2,223 passengers. Likewise, there were 1,692 males out of all 2,223 passengers. So when we simplify that fraction, we do in fact get the same value we had before, which was the 332 over the 1,692. So whether we make use of the table on the previous page or the conditional probability formula here, we end up with the same outcome. Let's look at another example. Suppose we have a box that contains 8 red balls and 4 white balls, and our plan is to select 2 balls without replacement. And we'll assume that at each selection, any ball in the box is equally likely to be selected, and we're interested in determining the probability that both balls are red. So we're looking for the probability that the first ball is red and the probability that the second ball is red. So we could view this as an intersection of 2 events, or we could view this as 2 successive selections where we can use the slot method from Chapter 1 and look at the number of possible ways to select the first ball red followed by selecting the second ball red. But with that second ball, keep in mind that there's a condition here. When we're looking to select that second ball and we want it to be red, this is given that we've already selected the first ball to be. So in particular, the probability of the first ball being red is 8 out of 12, since there's 8 red balls out of 12 total. And then when we get to the second slot, we've already selected 1 ball. So that means there's only 11 balls that remain, and only 7 of them are red. So we'll 7 over 11 to give us a 14 over 33. So it's important to recognize that embedded into this question is really a conditional probability, that 7 over 11. Although it's worth knowing that there is an alternate method to do this problem. We could use combinations. We could view this as just saying we want the probability where both are red, and there's 8 choose 2 ways to pick the 2 red balls, and there are 12 choose 2 ways to pick 2 balls from 12 without restriction, giving us the same value of 14 over 33. Now, Theorem 2.9 essentially formalizes what we saw in that last example, that if we have 2 events, A and B, in a sample space, and if we knew that the probability of A is non-zero, then we can write the probability of A intersected with B as the probability of A times the probability of B given A. To see where this comes from, remember that the probability of B given A was equal to the probability of A intersected with B over the probability of A. And since the probability of A is non-zero, we can solve this expression algebraically to get that the probability of A intersect B is equal to the probability of A times the probability of B given A, which is what the theorem tells us. Alternatively, if the probability of B is non-zero, we can get an equivalent expression that the probability of B intersected with A is equal to the probability of B times the probability of A given that B has already occurred. The example we did about selecting 2 balls that were red from the box of 12 is a demonstration of this Theorem 2.9. We can generalize this to 3 events, A, B, and C, in S, so long as the probability of A intersected with B is non-zero, to get the following in Theorem 10. The probability of the intersection of A, B, and C is the same as the probability of A times the probability of B given A times the probability of C given that A intersect B has occurred. Let's look at that as an example. And I should mention If you want to read a proof of this, I'll refer you to your text. So for this example, we'll suppose we randomly select 3 cards without replacement from a standard deck of 52, and we're going to apply Theorem 2.10 to find the probability that all 3 cards are spades. And we'll define events as follows. Event A is that the first card is a spade, event B is the second card is a spade, event C is the third card is a spade. And so we're looking for the probability of A intersected with B intersected with C. And much like the previous example with the balls, we can think of this as 3 slots that need to be filled, and each slot we can find its associated probability and take their product, but their associated probabilities are conditional probabilities. So the first slot is the probability of getting a spade, which is 13 out of 52. The second slot is the probability of getting a spade, given that we already selected one, so there are only 12 spades left out of 51 cards. And then lastly, the third slot, we have 11 spades left, but only 50 cards remaining in our deck. So we have the product of those 3 probabilities, which gives us 11 over 850. Again, it's worth knowing that we could use an alternate method for this problem, the probability that all 3 cards are spades. We could use combinations. There are 13 choose 3 ways to select 3 out of the 13 spades, and there are 52 choose 3 ways to select 3 cards from 52. That, if we do the computation, leads us to the same probability of 11 over 850. And this concludes our discussion of conditional probability.